Okay. Okay. Hi, everyone. I'm actually George as well. I mean, I go with George in English. So I'm going to be talking about spontaneously scalarized black holes today, but in particular about stable spontaneously scalarized black holes. So Julia Ventagli talked this morning actually about neutron star scalarization and said a few things about scalarization. So I'm not going to spend a lot of time explaining what it is. This talk is mostly based on these two papers that I'm having here. So let's start with scalarization. What do we do here and what is scalarization? Basically, we start with the Einstein-Hilbert action and we add an extra degree of freedom in the form of a scalar field. So for example, in action 1, we have the kinetic term for the scalar field, and we have this term over here, the phi squared term that acts as an effective mass term, essentially. And then we also have this gamma term as well. So actually, action 1 is part of the Hordetsky theory, which describes the most general setup that leads to second-order equations of motion with an extra scalar degree of freedom. And scalarization, as Julia said, at a linear level corresponds to a tachyonic instability phenomenon, basically. So what happens is that the effective mass for the scalar field, which in my talk, I will consider to be given by this boxed relationship here. So for simplicity, I'm taking the bare mass of the field and the gamma term to be 0. So this effective mass can become negative when alpha is positive, especially close to very compact objects, because that term, the Gauss-Bonnet term, where the coupling alpha appears, becomes very dominant there because it's a function of r squared, the Ricci squared and the Riemann squared, and the Ricci scalar squared. So when this mass becomes really negative, what happens is that a scalar profile develops and the black hole acquires what we call scalar hair, basically. So for example, in this particular model here, given by action 1, one can try and find spherical black hole solutions and static black hole solutions. That's obviously the simplest scenario. You can also look for rotating black holes, etc. But for static and spherically symmetric black holes, you can consider the metric 2, for example. And then you can say, okay, I want to have a horizon at some distance, and then I also want my solutions to be asymptotically flat. So if you impose those two things, will you be able to find solutions, black hole solutions? And the answer is yes. And those solutions, we usually use two quantities to characterize them: the mass, which corresponds to the ADM mass of the solution, and the scalar charge. By scalar charge, we mean the coefficient of 1 over r term in the expansion of the scalar field at infinity. So that's like the electric charge in electromagnetism, which is the 1 over r coefficient of the potential, of the expansion of the potential. And so what I have in these two plots here is essentially the same thing. So the plot to the right is a zoomed in version of the plot in the left. And these lines appearing in these plots correspond to black hole solutions with some particular charges, scalar charges, and some particular masses. So one thing that this tells you is that the charge essentially is of secondary nature because it actually depends on the mass of the black hole. And actually, a characteristic that appears in these plots and ends up being important is that for different choices of beta, and beta, I remind you, is the Ricci coupling, is this coupling right here, actually affect the way these curves tilt. Okay, so you see that when you start cranking up beta on the positive side of the spectrum, obviously, of course, you could choose negative betas as well, but they're not as important, and I'll explain why. So when you start cranking up beta, you get this curve starting to tilt to the left. So you get larger scalar charges for smaller masses. And this is an interesting characteristic because it sometimes can be associated with the stability of the solutions. And that's what I'm going to talk about now. It has been shown that when you only consider the alpha, the Gauss-Bonnet coupling, which can trigger the scalarization, this is the term that actually triggers the scalarization, the black hole solutions you retrieve are actually unstable. We will see now that this beta coupling can actually stabilize the solutions. So this particular model, given an expression 1, actually is interesting for two more reasons. So first of all, it is consistent with a late time cosmological attractor, which is something that scalarization models usually are not able to satisfy. So if you include this Ricci, you end up having a scalar field that vanishes cosmologically. So you don't end up with a scalarized universe or whatever else. And also this particular model, and that relates to what Julia talked about this morning, actually prevents neutron stars from scalarizing, or at least it reduces the parameter space where you expect to find neutron stars scalarizing. So it can lead to the avoidance of the very strict binary pulsar constraints, which would render these models unphysical. So the question that, some more questions that we could ask is, are these black holes stable now? And what about the hyperbolicity for the hyperbolic formulation of the equations? Because it also has been shown that when you only consider the Gauss-Bonnet coupling, which is enough to trigger scalarization, you end up having hyperbolicity of the scalar perturbation equation breaking down, which is obviously a bad thing. Okay, so about stability, what one can do is consider radial perturbations to the numerical background, which corresponded to these plots I showed you before. So you consider perturbations to the metric and to the scalar field. And then at least for a spherically symmetric problem, it is possible to decouple the equations and actually end up with a perturbation equation only for the scalar field, which you can then solve and look for quasi-normal modes, unstable modes, and whatever else you want to look for. Even before you do that, you can actually recast equation 5 into a Schrödinger type equation where you can identify an effective potential. And a condition about unstable modes we know to be associated to this integral of the effective potential over the whole space-time being negative. So when this condition is satisfied, you know that there should be unstable modes. When this condition is not satisfied, however, you're not guaranteed that no unstable modes are present. So you do actually have to do the proper analysis. But even at this point, it is evident actually that when you start cranking beta up, what happens is that the region of the effective potential that's negative actually shrinks and then vanishes. So that's a good indication that beta actually could help with the stability. But then what one needs to do is actually solve this equation right here by taking phi to be some function that's independent of time multiplied by some exponential of the frequency, and then just solve this for the frequency using the appropriate boundary conditions, which are ingoing waves at the horizon and outgoing waves at infinity, basically. And if you do that, so this plot corresponds to those solutions. So in this plot, we have the purely imaginary modes of the scalar field, which would correspond to unstable solutions. And one can see that so these values 0, 0.7, 0.9, and 1.2 correspond to beta. So one can see that when you start cranking up beta, you actually work against unstable modes. And at some point, which is around beta being 1.2 or something like that, you stop finding unstable modes altogether. So the black hole solutions that correspond to the left tilting curves in these plots are actually stable. Okay, so these blue parts. Yeah, thank you. Then the other question is, what about the hyperbolicity? Because as I said, it has been shown that in the absence of the Ricci term, the hyperbolicity of the scalar perturbation equation can actually break down. So what happens is, again, that when beta is positive and you start cranking it up, you end up reducing the region of the parameter space where hyperbolicity breaks down. So not only you end up having stable solution, but also the hyperbolicity of the equation is improved, which is obviously a very positive thing. So to conclude, this particular model here has many interesting characteristics. First of all, it's consistent with cosmology. It can lead to evasion of the binary pulsar constraints that restrict these models. It also leads to stable solutions, and it improves the hyperbolicity. And in terms of things that one could look further, is what happens with the quasi-normal modes in general. So one needs to explore what happens with quasi-normal modes, not just imaginary modes or whatever else, because that's a little bit more complicated, actually. And it's important to take a deeper look into the well-posedness, where you consider the hyperbolicity of the Einstein equations in addition to the scalar equation. Yeah, so that's pretty much it. Thank you. So if you have any questions, go ahead, please.
Cool. Perfect timing again. Excellent work. Okay, so I'll take the liberty of first question again. So I was wondering about what happens if you were to add in a cosmological constant.
So if you add a cosmological constant, actually, the black hole solutions you get are no longer asymptotically Schwarzschild, right? We have actually explored that. It is possible for a negative cosmological constant to get black hole solutions. For a positive cosmological constant, the things are more complicated. But at least, so we're very interested in these models because we can, in a sense, these are asymptotically Schwarzschild, asymptotically flat, and we can actually hope to have gravitational wave signatures coming from events that pertain to this theory. So maybe, so the question you're asking could be interesting, maybe from an ADS-CFT point of view, but I don't know if it would be that interesting from a gravitational waves perspective.
Yeah, I expect it would make little difference for gravitational waves. But yeah, I was just wondering if it affected any of the mathematical stability arguments. But it sounds like it's pretty good for, at least for negative.
For a negative cosmological constant, yeah, it would be, you actually end up having solutions. But again, I don't know if that would mean anything different for gravitational waves, which is the motivation behind this work.
Yeah, thank you.
But that's interesting, actually. I don't know if people have looked into the ADS-CFT implications. That's a good question. I don't know.
Cool. So perhaps something to wait for BitGrav 23. Then.
Yeah.
Cool. We have a question. When you say that it's consistent with late-time cosmology, you mean if we interpret the scalar field as dark energy? And what about instabilities in inflation? And there's some reference to work.
Okay, yeah, good. Both good questions. So unfortunately, I don't think I have enough time to explain this in detail, but no, I'm not considering this to be the source of dark energy. I'm considering this in addition to dark energy. So I'm considering this model on a cosmological background, so on an FLRW background or whatever else, where the scalar field depends on time, but it doesn't act as dark energy. And the question about inflation is actually very interesting. But at least the analysis we had done cosmologically actually breaks down much sooner than the time scale that would correspond to inflation. So you would need a more complete theory that would basically complete this in the ultraviolet in order to be able. So this can only be seen as an effective part of a larger theory, is what I'm saying, that actually breaks down those time scales. So yeah, it's not proper to describe the inflation part of the cosmology.
Thank you. I think we'll have to move on now. But any further discussion, please do move over to Slack. I think that's quite an interesting topic to delve a bit more into.